We have time, a lot of time, about 5 billion years, give or take. That is the current estimate for when the main fuel source in our star, the Sun, will begin to run out. The hydrogen at its core, which has been fusing into helium for the last 4.6 billion years, will be mostly spent. The delicate balance between gravity pulling everything inward and the outward pressure from nuclear fusion will break. Its gravity will start to win, the core will compress and heat up. This new intense heat will push the Sun's outer layers outward, expanding them on a scale we can barely comprehend. Our star will become a red giant. Its diameter could swell to over 200 times its current size. Its expanding edge will consume Mercury first, then Venus. The Earth's fate is less certain, but the outcome is the same. Even if our planet is not directly swallowed, the proximity to this new enormous star will be devastating. The Sun's luminosity will increase thousands of times. The surface temperature on Earth will rise to well over 1,000 degrees Celsius. Our oceans, the cradle of all life we know, will boil away completely. The atmosphere will be stripped by the intense solar wind. The rock of the continents will melt into a global ocean of magma. Eventually, the Earth will likely be vaporized, its constituent atoms of iron, silicon, oxygen, and everything else becoming part of the Sun's bloated outer atmosphere. But it feels like an absolute end. The final, irreversible destruction of our home. But it is not. It is just one step in a much larger, much older process. The universe wastes nothing. The atoms that once made up our planet will, after the Sun sheds its outer layers, be returned to the cosmos. They will float in the dark for millions of years until gravity pulls them into a new cloud of gas and dust. From that cloud, new stars and new planets will be born. The end of our world is the seed of another. This is the fundamental rule of the cosmos. Everything is recycled. Number 21, Planet Migration and Destruction, the Solar System Shuffle. A planetary system is not a static, clockwork machine. Over 99% of all species that have ever lived on Earth are now extinct. Our own solar system likely had more planets in its early history than it does today. Computer models show that the formation of giant planets like Jupiter and Saturn is a messy business. These behemoths can migrate, moving inward toward their star, or outward into the colder reaches. The Grand Tack hypothesis suggests Jupiter formed farther out and then moved inward to about where Mars is today before Saturn's gravity pulled it back out to its current orbit. During this journey, it would have acted like a gravitational wrecking ball. Its immense gravity would have thrown any smaller, early-generation planets in its path into new, chaotic orbits. Some would have been flung out of the solar system entirely, others would have been sent spiraling into the Sun. The material of these destroyed worlds was simply reabsorbed by the young Sun, adding to its mass. This is not a rare event. When we look at other star systems, we find many hot Jupiters. These are gas giants orbiting their stars at incredibly close distances, much closer than Mercury orbits our Sun. They could not have formed there. The heat and solar wind from the parent star would have blown away the gas needed to create such a massive planet. So they must have formed farther out and migrated inward. As they did, they would have cleared a path, ejecting or consuming any smaller rocky planets that stood in their way. The planets we see today are the survivors of a violent early history. The rest have been recycled. Even planets that survive this initial phase are not safe forever. Tides play a huge role. A large planet orbiting very close to its star will raise a tidal bulge on the star itself. The star's rotation then drags this bulge forward, which in turn pulls on the planet, causing it to lose orbital energy. Over millions of years, the planet spirals closer and closer to its star until it is torn apart by gravity or consumed whole. We can sometimes see the chemical evidence of this. When a star consumes one of its rocky planets, the heavy elements from that planet, like lithium and iron, are deposited into the star's outer layers. Astronomers can detect a temporary spike in these elements in the star's spectrum, a chemical ghost of a devoured world. And then there is the star's own evolution. As our sun becomes a red giant, it will consume the inner planets. Their matter will be incorporated into the star. When the sun finally sheds its outer layers to form a planetary nebula, the atoms that once made up Mercury, Venus, and perhaps Earth will be cast out into interstellar space. This material, now enriched with elements forged inside the sun, will mix with the surrounding gas and dust. This is the ultimate planetary recycling. A planet is born from a disk of gas and dust around a star. It lives for billions of years. Then its star dies and returns the planet's material to the, interstellar medium, where it will eventually become part of a new star and new planets. The iron in our blood was forged in a star, but the rock beneath our feet may have been part of an earlier planet, destroyed and reformed. Number 20, white dwarf crystallization, a slow release of energy. When a star like our sun dies, it leaves behind a core of super dense matter called a white dwarf. This object is about the size of the Earth, but contains about half the mass of the sun. A single teaspoon of white dwarf material would weigh several tons. These objects are incredibly hot at first, over 100,000 degrees Celsius, but they have no internal fuel source. They are cosmic embers, slowly cooling over trillions of years. This cooling process is not a simple fade to black. Something remarkable happens. The core of a white dwarf is mostly carbon and oxygen squeezed together under immense pressure. As it cools, the pressure and temperature reach a point where the carbon and oxygen atoms lock into a rigid lattice structure. The white dwarf begins to crystallize from the inside out. It is turning into a gigantic Earth-sized diamond. The largest known diamond in the universe is a crystallized white dwarf star named BPM 37093, nicknamed Lucy, after the Beatles song. It is estimated to be a diamond of 10 billion trillion carats. This process of crystallization is a phase transition, like water freezing into ice. And just like freezing water releases latent heat, the crystallization of a white dwarf releases a tremendous amount of gravitational potential energy as heat. This process significantly slows down the cooling of the white dwarf. It essentially provides a new temporary energy source that keeps the dead star shining faintly for billions of years longer than it otherwise would. The slow release of energy is a form of recycling. The energy that was locked up in the structure of the star's core during its life is slowly released back into the universe as heat and light. This has a profound impact on our understanding of the age of the universe. Astronomers use the coolest, faintest white dwarfs as cosmic clocks. By measuring their temperature, they can calculate how long they have been cooling. This gives a minimum age for the star clusters they live in, and by extension, the universe itself. Initially, calculations did not account for the heat released by crystallization. This led to an age paradox where some star clusters appeared to be older than the universe itself. When scientists included the energy released by this massive crystallization process, it added 2 to 3 billion years to the cooling time of these old white dwarfs. The paradox was solved. The slow, patient recycling of energy within these dying stars corrected our measurement of cosmic time. These stellar diamonds are not just beautiful concepts, they are crucial to understanding our universe's history. Number 19, molecular clouds, the cold cradles of stars. Most of space is an incredibly empty vacuum, but it is not completely empty. Between the stars, there are vast, dark clouds of gas and dust. These are the giant molecular clouds. They are colossal. A single cloud can be hundreds of light years across and contain enough material to form 1 million stars like our sun. They are also incredibly cold, just a few degrees above absolute zero. At these temperatures, atoms can clump together to form molecules, mostly molecular hydrogen H2, but also more complex molecules like water, carbon monoxide, and even simple organic compounds. These clouds are the raw material for new stars. They are the great recycling depots of the galaxy. The material within them is not primordial. It is a mix of the original hydrogen and helium from the Big Bang, along with heavier elements forged inside previous generations of stars. These heavier elements were spewed into space by stellar winds and supernova explosion. Over millions of years, this enriched material drifts through the galaxy and eventually collects in these cold, dense clouds. Gravity is the engine of this recycling process. Within a molecular cloud, there are regions that are slightly denser than their surroundings. Where gravity begins to pull these denser clumps together. As a clump collapses, it gets hotter and denser, forming a protostar at its center. This is how new stars are born. The cloud is the parent, and its material is recycled into a new generation of stellar children. But the process is not 100% efficient. When a group of massive hot stars forms within a molecular cloud, their intense ultraviolet radiation and powerful stellar winds begin to blow away the surrounding gas and dust. This process carves out huge cavities in the cloud and can eventually dissipate it entirely. This is a form of negative feedback. The birth of stars destroys the very nursery that created them. However, this is also a crucial part of the cycle. By blowing the gas away, the stars are preventing all of it from being locked up in one generation of stars. They are ensuring that there is raw material left over for future star formation elsewhere in the galaxy. The shock waves from these young, massive stars can also trigger new star formation. As a shockwave plows through the molecular cloud, it compresses the gas, creating new dense clumps that can then collapse under their own gravity. It is a chain reaction. The birth of one group of stars triggers the birth of the next. The molecular cloud is not just a passive reservoir, it is a dynamic environment where the life and death of stars are intricately linked, a continuous cycle of collapse, creation, and dispersal. Number 18, protostellar outflows, a star's first breath. When a new star is forming, it does not just passively accrete material. In its earliest stages as a protostar, it is a chaotic and violent object. As gas and dust from the surrounding molecular cloud fall inward onto a rotating accretion disk around the protostar, something incredible happens. A portion of that infalling material is not consumed by the star. Instead, it is channeled by powerful magnetic fields and ejected at tremendous speeds from the star's poles. These are called protostellar outflows or bipolar jets. These jets are cosmic fire hoses shooting out streams of gas at hundreds of kilometers per second. They can extend for light years, ramming into the surrounding molecular cloud. Where they collide with the cloud, they create beautiful and complex structures called Herbig-Haro objects, which glow as the shockwave heats the gas. This process is a crucial form of recycling right at the moment of a star's birth. The protostar is essentially throwing away a significant fraction of the material that is trying to fall onto it. It might seem wasteful, but it is essential for the star's own survival. These jets carry away angular momentum from the accretion disk. Without this release valve, the disk would be spinning too fast for material to actually fall onto the star. The protostar would choke on its own fuel. The outflows allow the accretion process to continue, enabling the star to grow to its full size. These outflows have a profound impact on the surrounding stellar nursery. They inject a huge amount of energy and momentum into the molecular cloud. This turbulence can prevent other parts of the cloud from collapsing too quickly, regulating the pace of star formation. It is a self-regulating system. Too much star formation creates powerful jets that stir up the cloud and slow things down. Furthermore, the material in these jets is recycled back into the interstellar medium. It is not fundamentally changed, but its journey is important. It is blasted far away from its parent protostar, mixing with other parts of the molecular cloud. The shockwaves from these jets can also compress nearby gas, potentially triggering the collapse of new stars. So, the very process of one star's birth, its first violent breaths, can sow the seeds for the next generation of stars. It is a local, immediate form of recycling that shapes the evolution of entire star-forming regions. Number 17, starbursts, a frenzy of creation and destruction. Most galaxies, like our Milky Way, form stars at a relatively steady, slow pace. A few new stars every year. But some galaxies go through a period of intense, rapid star formation known as a starburst. During a starburst, a galaxy can form stars at a rate hundreds or even thousands of times greater than the Milky Way. This is not sustainable. A starburst is a short-lived, violent phase in a galaxy's life, and it is one of the most intense recycling events in the universe. Starbursts are usually triggered by a major disturbance, most often the collision and merger of two gas-rich galaxies. As the galaxies collide, their huge clouds of molecular gas are slammed together and compressed. This massive compression triggers a galaxy-wide wave of gravitational collapse, leading to the simultaneous birth of millions of stars, including a huge number of very massive, hot blue stars. These massive stars live fast and die young. They burn through their fuel in just a few million years, a mere blink of an eye in cosmic terms. When they die, they explode as supernova. Because so many massive stars were born at the same time, they also die at roughly the same time. A starburst galaxy is therefore racked by a constant overlapping barrage of supernova explosions. This creates something called a superwind. The combined energy of thousands of supernovae creates a powerful galaxy-scale wind that blows outward from the starburst region. This wind is so strong that it can push gas completely out of the galaxy and into intergalactic space. The wind is filled with heavy elements, the carbon, oxygen, and iron that were forged inside the short-lived massive stars and then released in their supernova deaths. This is recycling on a galactic scale. The starburst phase rapidly converts a galaxy's raw gas into stars. Those stars then quickly process that gas into heavier elements, and then the superwind ejects a significant portion of this enriched gas out of the galaxy. This pollutes the intergalactic medium with heavy elements, making them available for future generations of galaxies. It also removes the fuel for star formation from the galaxy, effectively quenching the starburst. The galaxy then settles down into a quieter phase, its burst of creative and destructive energy spent. The starburst is a dramatic cycle of consumption, enrichment, and expulsion that fundamentally changes both the galaxy itself and the cosmic environment around it. Number 16, brown dwarfs, the universe's holding pens. Not every collapsing cloud of gas has what it takes to become a star. If the collapsing clump has a mass less than about 8% of our sun's mass, or about 80 times the mass of Jupiter, its core will never get hot and dense enough to ignite sustained hydrogen fusion. The object will heat up and glow dimly for a while from the heat of its own contraction, but it will never become a true star. These are the brown dwarfs, often called failed stars. Brown dwarfs occupy a strange middle ground between planets and stars. They are too massive to be considered planets, but not massive enough to be stars. They are incredibly faint and difficult to detect, mostly glowing in the infrared part of the spectrum. For a long time, they were purely theoretical. The first confirmed brown dwarf was not discovered until 1995. We now know that they are very common, possibly as common as stars. From a recycling perspective, brown dwarfs are the universe's holding pens. They are made of the same material as stars, mostly hydrogen and helium mixed with a small amount of heavier elements from the interstellar medium they formed from. But because they do not ignite fusion, they do not process this material, they do not turn hydrogen into helium or create new, heavier elements. They simply lock that material away. They hold onto this primordial and recycled gas for incredibly long periods. While a massive star might live for a few million years and a sun-like star for 10 billion years, a brown dwarf will exist for trillions of years. They are some of the longest-lived objects in the universe. They just sit there slowly cooling and fading over cosmic time. So, are they a dead end for cosmic material? Not necessarily. Over immense timescales, many things can happen. A brown dwarf could be part of a binary system and eventually have its material stripped away by a companion star. It could collide with another object. More importantly, they contribute to the overall mass of a galaxy, influencing its gravitational dynamics and the orbits of other stars. They are a dark, quiet component of the cosmic inventory. They are not active recyclers in the way stars are, but they are a crucial part of the storage side of the equation. They represent a vast reservoir of unprocessed material held in reserve that may one day, through some future cosmic event, be returned to the great cycle of stellar birth and death. Number 15, protoplanetary disks, the birthplace of worlds. When a new star forms from a collapsing cloud of gas, not all the material falls directly onto the star. Because the original cloud has some slight rotation, conservation of angular momentum causes the material to flatten into a spinning disk around the protostar. This is a protoplanetary disk. It is from this disk that planets, moons, asteroids, and comets will form. These disks are the direct link between the interstellar medium and planetary systems. They are made of the same stuff as the molecular cloud, about 99% gas, mostly hydrogen and helium, and 1% dust. This dust is not like household dust. It consists of tiny microscopic grains of silicates, carbon compounds, and ices. These dust grains are the seeds of planets. They are themselves recycled material, the ash from long-dead stars. Within the disk, these tiny dust grains begin to stick together. First through electrostatic forces, then through gentle collisions, they form larger and larger clumps. This process is called accretion. Clumps grow into pebbles, pebbles into rocks, rocks into kilometer-sized planetesimals. These planetesimals are large enough to have significant gravity, and they begin to pull in other, smaller objects. The largest of these planetesimals become planetary embryos, and eventually, after millions of years of collisions and mergers, they become full-fledged planets. This entire process is a form of sorting and recycling. The temperature in the disk varies with distance from the central star. Close to the star, it is too hot for ices to condense. Only rocky materials and metals can solidify. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are small and rocky. Farther out, beyond the frost line, it is cold enough for water ice, ammonia ice, and methane ice to form. This adds a huge amount of solid material to the disk, allowing the formation of giant planetary cores that can then capture the abundant hydrogen and helium gas to become gas giants like Jupiter and Saturn. The protoplanetary disk does not last forever. After a few million years, the process of planet formation is mostly complete. The intense radiation and stellar wind from the young central star will blow away any remaining gas and dust. What is left is a young and often unstable planetary system. The material of the interstellar medium has been recycled and transformed. A diffuse cloud of gas and dust has been concentrated and organized into a small number of large, complex bodies. The stage is set for the next phase of cosmic evolution, the billions of years of planetary life and eventual death. Number 14, cosmic ray spallation high-speed alchemy. The space between stars is not entirely empty. It is filled with a constant shower of high-energy particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. These are cosmic rays. They originate from violent cosmic events like supernova explosions and the jets from supermassive black holes. When these incredibly energetic particles smash into other atoms, they can break them apart. This process is called cosmic ray spallation, and it is a unique form of cosmic recycling and alchemy. Stellar nucleosynthesis, the fusion inside stars, is very good at making certain elements. It can fuse hydrogen into helium, helium into carbon, and so on, all the way up to iron. Supernovae and neutron star mergers can create elements heavier than iron, But there are a few light elements that are mostly skipped over in these processes. Lithium, beryllium, and boron are very fragile. They are actually destroyed, not created, in the hot, dense cores of most stars. Yet, we find these elements in the universe. So, where do they come from? The answer is cosmic ray spallation. As a high-energy cosmic ray, say a proton, travels through space, it might collide with a larger atom in the interstellar gas, perhaps a carbon or oxygen nucleus. The impact is so violent that it shatters the larger nucleus, knocking off protons and neutrons. The fragments left behind are smaller, lighter nuclei. This is how most of the universe's lithium, beryllium, and boron are created. A carbon nucleus, 6 protons, 6 neutrons might be struck by a cosmic ray and break apart into a boron nucleus, 5 protons, 5 neutrons, and other fragments. This is a fundamentally different kind of element creation than what happens in stars. It is not fusion building up, but spallation breaking down. It is a slow, steady process that happens continuously throughout the galaxy. The atoms floating in interstellar space are constantly being bombarded and transformed by this cosmic radiation. It is a subtle but crucial part of the recycling of matter. Larger, more common elements, which were themselves forged in stars, are broken down into smaller, rarer elements. This process also affects the Earth. When cosmic rays hit atoms in our upper atmosphere, they create a cascade of secondary particles and produce rare isotopes like carbon-14. Carbon-14 is then absorbed by living organisms. Since it decays at a known rate, we can measure the amount of carbon-14 in ancient organic material to determine its age. This is the basis of radiocarbon dating. So, this strange form of cosmic recycling, this high-speed alchemy happening in the vastness of space, provides us with one of our most powerful tools for understanding the history of our own planet. Number 13, accretion disks, the cosmic grinder. Accretion disks are one of the most powerful and efficient recycling mechanisms in the universe. They form whenever a large amount of matter is drawn by gravity toward a central object, like a young star, a white dwarf, a neutron star, or a black hole. Because the infalling material always has some rotation, it does not fall straight in. Instead, it flattens into a spinning disk, much like a protoplanetary disk, but often far more extreme. An accretion disk around a compact object like a black hole is a place of incredible violence. As gas spirals inward, different layers of the disk rub against each other at immense speeds. This friction generates a tremendous amount of heat. The gas in the inner parts of the disk can be heated to millions of degrees, causing it to glow brightly in X-rays. This is how we can see black holes. We do not see the black hole itself, but the superheated material in the accretion disk just before it crosses the event horizon. This process is a remarkably efficient way of converting gravitational potential energy into radiation. As matter falls deep into a gravity well, it releases energy. An accretion disk can convert up to 40% of the mass of the infalling material into energy. For comparison, nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. This makes accretion disks around black holes the most luminous objects in the universe. A single quasar, which is a supermassive black hole actively feeding on an accretion disk, can outshine its entire host galaxy of billions of stars. This intense radiation has a huge impact on the surrounding environment. It can heat up and ionize gas for thousands of light years around, influencing star formation in the host galaxy. The accretion disk is not just a passive funnel, it is an engine that processes material and broadcasts its energy across the cosmos. The material that enters the disk is fundamentally transformed. It is heated to a plasma state, its atoms stripped of their electrons. It is subjected to intense magnetic fields and gravitational forces. It is completely torn apart and homogenized before it finally disappears into the central object. Stars, planets, asteroids, and gas clouds that get caught in an accretion disk are ground down to their constituent particles. Their substance is recycled and their energy is released back into the universe in a final brilliant blaze of glory. Number 12. Tidal stripping gravity's slow theft. Galaxies are not isolated islands, they are part of a cosmic web clustered together by gravity. When a large galaxy and a smaller dwarf galaxy have a close encounter, the larger galaxy's immense gravity can have a dramatic effect on the smaller one. The side of the dwarf galaxy closer to the large galaxy feels a much stronger gravitational pull than the far side. This difference in force, known as a tidal force, can stretch the smaller galaxy. If the encounter is close enough, this tidal force can be strong enough to pull stars and gas out of the dwarf galaxy. This process is called tidal stripping. It is a slow, relentless form of galactic theft. Over multiple passes, the larger galaxy can completely dismantle its smaller companion. The stolen stars and gas are not lost. They are incorporated into the larger galaxy, forming long, faint streams of stars that orbit in its halo. We can see this happening to our own Milky Way. The Sagittarius dwarf spheroidal galaxy is currently in the process of being torn apart and consumed by the Milky Way. Astronomers have mapped out a huge stream of stars, the Sagittarius stream, that wraps around our galaxy, marking the trail of this ongoing disruption. These stars born in another galaxy are now becoming part of our own. Tidal stripping is a key way that large galaxies grow. They do not just form from one single giant cloud of gas. They are built up over billions of years by consuming their smaller neighbors. This is a form of recycling on a galactic scale. The processed material of one galaxy, its stars and enriched gas, is transferred and integrated into another. This process also recycles gas. When dwarf galaxies are stripped, their interstellar gas is pulled out and can mix with the gas in the halo of the larger galaxy. This stripped gas can then cool and rain down onto the disk of the larger galaxy, providing fresh fuel for a new round of star formation. A small galaxy that has used up most of its gas and stopped forming stars can be rejuvenated, in a sense. Its remaining stars are donated to a larger system, and any leftover gas is put back into the active star-forming cycle of its new home. It is a demonstration of the cosmic food chain where the large grow by slowly digesting the small. Number 11, the intergalactic medium, a hidden reservoir. The vast spaces between galaxies are not a perfect void. This region, known as the intergalactic medium IgM, contains a tenuous hot plasma of hydrogen and helium. While the density is incredibly low, just a few atoms per cubic meter, the sheer volume of intergalactic space means that the IgM contains a huge amount of matter. In fact, it is believed that the IgM contains as much or even more baryonic matter, the normal matter that makes up stars and planets, than all the galaxies combined. This material is not just primordial gas left over from the Big Bang. It is also a repository for material that has been recycled out of galaxies. Powerful superwinds from starburst galaxies and jets from supermassive black holes blow huge amounts of gas out of their host galaxies and into the IgM. This gas is not just hydrogen and helium, it is enriched with the heavy elements forged inside the stars of those galaxies. So the IgM is a vast hidden reservoir of recycled element-rich material. For a long time, it was thought that this expulsion was a one-way trip. But we now know that this is not the case. Galaxies are constantly accreting gas from the IgM. This can happen in a few ways. Cold, dense filaments of gas from the cosmic web can flow directly into galaxies, a process called cold mode accretion. This provides a steady stream of fuel for star formation. Additionally, the hot enriched gas that was previously blown out of a galaxy can cool over billions of years and eventually fall back into the galaxy it came from, or into a neighboring one. This creates a galaxy-wide recycling loop. A galaxy forms stars, which enrich its gas with heavy elements. Supernovae then blow this enriched gas out into the IgM. The gas spends hundreds of millions or even billions of years in this reservoir before cooling and raining back down onto the galaxy to fuel the next generation of star formation. This cycle is crucial for sustaining star formation in galaxies like the Milky Way over cosmic time. Without this constant replenishment of fuel from the IGM, our galaxy would have used up all its available gas billions of years ago. The intergalactic medium acts as a giant buffer and storage tank, holding on to processed material and then slowly feeding it back to galaxies, ensuring that the process of cosmic creation can continue. Number 10, galactic fountains, a galaxy's gaseous breath. Inside a spiral galaxy like the Milky Way, star formation is concentrated in the thin disk. When massive stars in the disk explode as supernovae, they do not just enrich the surrounding gas. They also create huge, expanding bubbles of hot, million-degree gas. When many supernovae explode in the same region, these bubbles can merge and become powerful enough to break out of the galactic disk entirely. This creates a phenomenon known as a galactic fountain. Hot, enriched gas from the disk is blasted upward, out of the plane of the galaxy and into the galactic halo, the diffuse spherical region surrounding the disk. This gas can travel for tens of thousands of light years into the halo before it finally slows down. This is not a one-way trip. The gas does not escape the galaxy's gravity. As it travels through the halo, it begins to cool. Over a period of tens to hundreds of millions of years, the hot, diffuse gas radiates away its energy and condenses into cooler, denser clouds. Once it has cooled, gravity takes over again, and this gas begins to fall back down toward the galactic disk. It rains back down like a gentle cosmic drizzle. This galactic fountain model describes a continuous circulation of gas within a single galaxy. It is a local recycling process. Gas is taken from the disk, processed by stars, enriched with heavy elements, heated by supernovae, and ejected into the halo. It then cools in the halo and returns to the disk, ready to be incorporated into a new generation of stars and planets. This process has several important effects. It distributes heavy elements throughout the galaxy. A supernova might occur in one spiral arm, but the fountain can deposit its enriched gas onto a completely different part of the disk millions of years later. This helps to homogenize the chemical composition of the galaxy. It also regulates star formation. By removing hot gas from the disk, it can temporarily slow down star formation in that region. When the gas returns, it is cool and ready to form stars again, providing a fresh supply of fuel. The galaxy is breathing, exhaling hot gas into its halo and inhaling cool gas back into its disk in a self-sustaining cycle that lasts for billions of years. Number 9, stellar winds, a constant stream of lost atoms. Stars are not perfectly contained spheres of gas. They are constantly losing mass to space through a stream of charged particles called the stellar wind. Our own sun's solar wind is a continuous outflow of protons and electrons that travels through the solar system at hundreds of kilometers per second. This is a very gentle form of mass loss. The sun loses about 1/1,000,000th of an Earth mass every year. Over its entire 10 billion year lifetime, it will lose only a tiny fraction of its total mass this way. But for other types of stars, stellar winds are a major form of recycling. Massive, hot blue stars have incredibly powerful winds. Their intense radiation is so strong that it literally blows away their outer layers. A massive star can lose a significant fraction of its entire mass through its stellar wind long before it explodes as a supernova. In a star like Eta Carinae, one of the most massive stars in our galaxy, is losing mass at a rate of about one sun every few thousand years. The material lost in these winds is crucial. It is gas from the outer layers of the star, which has been processed by nuclear fusion. This wind carries newly created elements like carbon, nitrogen, and oxygen out into the interstellar medium. This is happening continuously throughout the star's life, not just at its death. Another important case is during the late stages of a sun, like star's life, when it becomes a red giant. As the star swells up, its surface gravity becomes very weak. This allows its outer layers to escape much more easily. The star develops a slow, dense, stellar wind that carries away a huge amount of its mass. This is the process that will eventually form a planetary nebula. The star is effectively dismantling itself from the outside in, returning its processed material to the galaxy. Stellar winds from all types of stars are constantly enriching the interstellar medium. They are a gentle, persistent form of recycling that operates alongside the more violent explosions of supernovae. The atoms that make up our bodies and our world were not all created in one cataclysmic event. Many of them, particularly elements like carbon and nitrogen, were likely created in the cores of stars and then gently blown out into space by these stellar winds, slowly accumulating in the clouds that would one day form our sun and the Earth. Number 8, planetary nebulae, the gentle death of sun-like stars. When a star with a mass similar to our sun reaches the end of its life, it does not explode. It dies a much slower, more graceful death. After its red giant phase, the star's outer layers are blown away into space by a powerful stellar wind. The hot, dense core of the star, the white dwarf, is left behind. The intense ultraviolet radiation from this hot core then ionizes the expanding shell of gas, causing it to glow. This beautiful glowing structure is called a planetary nebula. The name is a historical mistake. They have nothing to do with planets. Early astronomers with small telescopes thought their round shapes resembled gas giant planets. A planetary nebula is a final act of recycling. It is the star returning a large fraction of its mass back to the interstellar medium. This material is not just the original hydrogen and helium the star was made of. Over its billions of years of life, the star has been fusing elements in its core and in shells around the core. It has created new carbon, nitrogen, and oxygen. During the red giant phase, convection currents dredge up this newly forged material from the star's interior and bring it to the surface. It is this enriched material that is then expelled to form the planetary nebula. So, a planetary nebula is a cloud of freshly synthesized heavy elements cast out into the galaxy. Our own sun will create one in about 5 billion years. The atoms that currently make up the sun and any planets it has consumed will be spread out over a region of space a few light years across. This material will then slowly drift and mix with the surrounding interstellar gas and dust. Planetary nebulae are a major source of carbon and nitrogen in the universe. While supernovae create a lot of oxygen and heavier elements, these intermediate mass stars are the primary factories for the carbon that is the basis of all known life. The carbon in your DNA, the nitrogen in the proteins in your body were likely created inside a star, much like our sun, and then released into the galaxy in a beautiful, glowing planetary nebula billions of years ago. These structures, which last for only a few tens of thousands of years before they dissipate, are a vital link in the chain of cosmic recycling, ensuring that the building blocks of life are made available for the next generation of stars and planets. Number 7, core collapse, supernovae, the violent end of giants. Stars more than about 8 times the mass of our sun have a much more dramatic end. They live for only a few million years, fusing heavier and heavier elements in their cores. They create carbon, then neon, oxygen, silicon, and finally iron. Iron is the end of the line for stellar fusion. Fusing iron atoms does not release energy, it consumes energy. When the star's core becomes filled with iron, its energy source is cut off. Without the outward pressure from fusion, gravity wins catastrophically. The iron core, which is about the size of the Earth but contains more mass than the sun, collapses in on itself in less than a second. it shrinks from thousands of kilometers in diameter to just a few tens of kilometers. The collapse is so rapid and violent that the core overshoots its equilibrium point and bounces back. This rebound creates a colossal shockwave that blasts outward through the rest of the star. The shockwave tears the star apart in a titanic explosion known as a core collapse supernova, or a Type II supernova. For a few weeks, the single exploding star can outshine its entire host galaxy of billions of stars. This explosion is one of the most important recycling events in the universe. It blasts all the elements the star created during its lifetime out into space at incredible speeds. Huge quantities of oxygen, the third most abundant element in the universe, silicon and sulfur, are created and dispersed this way. The supernova explosion itself is also an incredible furnace. The energy of the shockwave is so immense that it triggers a brief, intense period of nuclear fusion in the star's outer layers. This explosive nucleosynthesis creates even more elements. It is also in the chaos of a supernova that some of the elements heavier than iron are formed through a process of rapid neutron capture. The supernova does more than just enrich the interstellar medium with heavy elements. The physical force of the explosion is just as important. The shockwave from a supernova can travel for thousands of light years through the surrounding space. When this shockwave encounters a giant molecular cloud, it can compress the gas, triggering the collapse of new stars. Our own sun and solar system were likely formed in this way. The chemical composition of ancient meteorites shows the presence of isotopes that could only have been formed in a nearby supernova explosion just before our solar system was born. The death of a massive star is not an end. It is a violent, creative act that seeds the galaxy with the raw materials for new worlds and provides the trigger for their creation. Number 6. Type Ia supernovae, the exploding dead stars. There is another completely different way a star can explode. This involves a white dwarf, the dead remnant of a sun-like star. If a white dwarf is in a binary star system with a normal companion star, its powerful gravity can pull material, mostly hydrogen and helium, from its companion. This material builds up on the surface of the white dwarf. As the layer of accreted material gets thicker and hotter, it can ignite in a runaway fusion reaction, causing a nova explosion. But sometimes the process is more stable. The white dwarf steadily gains mass from its companion. White dwarfs are supported by something called electron degeneracy pressure, which has a fundamental limit. A white dwarf cannot have a mass greater than about 1.4 times the mass of our sun. This is known as the Chandrasekhar limit. If the white dwarf accretes enough material to push its mass over this limit, electron degeneracy pressure can no longer support it. The star begins to collapse. This sudden collapse raises the temperature and pressure in the core of the white dwarf to the point where carbon fusion ignites. Because the material is so dense, the fusion is not a gentle burn. It is a runaway thermonuclear explosion. The entire white dwarf is consumed in a fraction of a second. This is a Type Ia supernova. Unlike a core collapse supernova, which leaves behind a neutron star or a black hole, a Type Ia supernova completely obliterates the white dwarf. Nothing is left behind. The entire star is converted into newly synthesized elements and blasted into space. These explosions are particularly important for creating a large fraction of the universe's iron. The explosion fuses the carbon and oxygen of the white dwarf into heavier elements, with a large yield of iron peak elements like nickel, which then radioactively decays into iron. The iron in your blood, which is essential for carrying oxygen, was likely created in one of these thermonuclear explosions of a dead star. Because all Type Ia supernovae are triggered when a white dwarf crosses the same mass limit, they all have a remarkably similar peak brightness. This makes them incredibly useful as standard candles for measuring cosmic distances. By observing how bright they appear, astronomers can calculate how far away they are. It was the observation of distant Type Ia supernovae that led to the discovery that the expansion of the universe is accelerating, driven by a mysterious force we call dark energy. These exploding dead stars not only recycle crucial elements, but they also helped us uncover the fundamental nature of the cosmos. Number 5. Neutron star collisions forge gold and platinum. When a massive star explodes in a core collapse supernova, it sometimes leaves behind an incredibly dense object called a neutron star. A neutron star packs the mass of one or two suns into a sphere just 20 kilometers in diameter. A single sugar cube of neutron star material would weigh as much as all of humanity combined. Sometimes two neutron stars are born in a binary system orbiting each other. Over millions of years, their orbits decay as they lose energy by emitting gravitational waves, ripples in the fabric of spacetime. They spiral closer and closer together until they finally collide and merge at a significant fraction of the speed of light. This merger is one of the most violent events in the universe. The collision creates an explosion called a kilonova, which is about 1,000 times brighter than a regular nova. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected the ripples from such a merger. An event named GW1, and telescopes around the world were able to pinpoint the source and observe the kilonova's light for the first time. The incredible importance of this event is what it creates. The material of the neutron stars is an exotic, super dense fluid of neutrons. When the two stars merge, a huge amount of this neutron-rich material is flung out into space. This environment, with its incredible density of neutrons, is the perfect place for a process called the R-process rapid neutron capture. Atomic nuclei are bombarded with a furious storm of neutrons, allowing them to rapidly grow into very heavy elements. For a long time, scientists debated where the heaviest elements in the universe, like gold, platinum, and uranium, were created. Supernova could not account for the observed abundances. The observation of GW 7817 provided the smoking gun. The light from the kilonova showed the clear spectral signature of newly synthesized heavy elements. It is now believed that the vast majority of all the gold and platinum in the universe was forged in the cataclysmic collisions of dead neutron stars. This is a profound form of recycling. Stars live and die, creating elements up to iron. They leave behind neutron stars. Those dead remnants then collide, and in their final violent merger, they create the rarest and most precious elements. This material is then sprayed out into the galaxy, where it gets incorporated into the next generation of molecular clouds, stars, and planets. The gold in a wedding ring or the platinum in a catalytic converter was not made in a star, but in the spectacular collision of two stellar corpses. Number 4, galactic cannibalism, when galaxies eat each other. The universe is a gravitational dance, and on the largest scales, galaxies are the dancers. And sometimes they collide. A collision between two large spiral galaxies does not mean that stars crash into each other. The distances between stars are so vast that direct stellar collisions are almost unheard of. Instead, the two galaxies pass through each other like ghosts, but their gravity has a huge effect. The galaxies are distorted, their spiral arms torn apart, and long tidal tails of stars and gas are flung out into intergalactic space. Over hundreds of millions of years, the two galaxies will be drawn back together by their mutual gravity. They will pass through each other again and again, each time losing energy and merging more completely. Eventually, after a billion years or so, they will settle down into a single, much larger galaxy. This new galaxy is usually an elliptical galaxy, a giant, disordered ball of older, redder stars with very little gas or active star formation. The beautiful, structured spirals have been destroyed, and their stars recycled into a new, larger entity. This process is often called galactic cannibalism. Our own Milky Way is a cannibal. We are currently in the process of consuming several smaller dwarf galaxies, like the Sagittarius dwarf galaxy, and we are on a collision course with our nearest large neighbor, the Andromeda Galaxy. In about 4.5 billion years, the Milky Way and Andromeda will begin their first pass. The sky will be filled with the distorted view of another galaxy. After a long and complex merger process, a new giant elliptical galaxy, sometimes nicknamed Milkometa, will be formed. This merger process is a powerful engine of recycling. While the stars themselves do not collide, the vast clouds of interstellar gas within the two galaxies do. They slam into each other at high speeds, compressing the gas and triggering a massive burst of star formation. The starburst will rapidly use up the available gas, creating a huge number of new stars. The most massive of these will quickly explode as supernovae, enriching the remaining gas with heavy elements. So a galaxy merger recycles galaxies themselves. It takes the ordered structures of two spiral galaxies and scrambles their stars into a new, larger system. It takes their cold, quiescent gas, triggers a violent and rapid conversion of that gas into a new generation of stars, and then settles into a new, quieter existence. It is the primary way that the most massive galaxies in the universe are built. Number 3, relativistic jets from supermassive black holes. At the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. These are objects with masses ranging from millions to billions of times the mass of our sun. When these black holes are actively feeding on gas and stars from their host galaxy, they form a brilliant accretion disk. But that is not all they do. As matter swirls into the black hole, powerful, twisted magnetic fields in the accretion disk can act like a cosmic particle accelerator. They can grab some of the infalling superheated plasma and launch it away from the black hole at nearly the speed of light. This material is ejected in two narrow, powerful beams from the poles of the black hole. These are relativistic jets. These jets are among the most energetic phenomena in the universe. They can be far larger than the galaxy they originate from, extending for hundreds of thousands or even millions of light years into intergalactic space. They are so powerful, they can inflate giant lobes or bubbles of hot magnetized plasma in the intergalactic medium. We can see these lobes with radio telescopes. They are the calling cards of an active galactic nucleus. The jets are a form of recycling and feedback on an immense scale. The black hole at the center of a galaxy is consuming material from its host. But in the process, it is ejecting a significant fraction of that material's energy, and some of the material itself, back out into the galaxy and beyond. This has a profound regulatory effect. The energy pumped into the galaxy by these jets can heat up the interstellar gas. This makes it harder for the gas to cool and collapse to form new stars. This is called AGN active galactic nucleus feedback, and it is a critical process in galaxy evolution. It can effectively shut down star formation in a galaxy, preventing it from growing too large. The black hole is regulating its own food supply. By heating the gas, it makes it harder for that gas to fall into the center, thus slowing down its own growth. The material in the jets is also a form of recycling. It is matter that has been processed through the extreme environment of an accretion disk and then blasted deep into the intergalactic medium. This carries heavy elements and magnetic fields far from the host galaxy, enriching the IGM. These jets are a crucial part of the cosmic circulatory system, connecting the very smallest scales, the region around a black hole, to the very largest scales, the spaces between galaxies, ensuring that energy and matter are not just locked away forever, but are redistributed throughout the cosmos. Number 2, Hawking radiation, the evaporation of black holes. Black holes are famous for being objects from which nothing, not even light, can escape. For a long time, it was thought they were truly the ultimate one-way street, the final graveyard for any matter or energy that fell into them. But in 1974, Stephen Hawking showed that this is not entirely true. Due to quantum mechanical effects near the event horizon, black holes are not completely black. They should glow very faintly, emitting a thermal radiation now known as Hawking radiation. The concept is based on the idea of virtual particles. In the quantum vacuum of empty space, pairs of particles and antiparticles are constantly popping into existence and then annihilating each other almost instantly. They exist for such a short time that they are virtual. Hawking realized that if a pair of these virtual particles is created right at the edge of a black hole's event horizon, it is possible for one particle to fall into the black hole while the other one escapes. The particle that escapes can no longer annihilate with its partner. To an outside observer, it appears as if the black hole has just emitted a particle. To conserve energy, the particle that fell into the black hole must have had negative energy relative to the outside universe. Since mass and energy are equivalent, E equals mc squared, the black hole's mass must decrease by a tiny amount. This process is incredibly, unimaginably slow. A black hole with the mass of our sun would take 10 to the power of 67 years to evaporate completely. A supermassive black hole with 1 billion solar masses would take around 10 to the power of 100 years, a number so large it is called a googol. This is vastly longer than the current age of the universe, which is a mere 13.8 billion years. But in the far, far future of the universe, when all the stars have burned out and all matter has decayed, this process will become significant. Hawking radiation represents the ultimate form of recycling. It is a mechanism by which the matter and information that were thought to be lost forever inside a black hole are slowly, painstakingly returned to the universe in the form of thermal radiation. As the black hole evaporates, it gets smaller and hotter, and the rate of radiation increases. In its final moments, it will release a final brilliant flash of gamma rays. The black hole will be gone. The material it consumed over eons will have been converted back into energy and returned to the cold, empty universe of the far future. It is the final, complete closing of the cosmic recycling loop. Number 1. The Great Cosmic Reset, the Big Bounce Theory. The standard model of cosmology, the Big Bang Theory, tells us that the universe began from an infinitely hot, infinitely dense point called a singularity. But a singularity is where our laws of physics break down. It is a point of infinite values, which usually tells physicists that their theory is incomplete. What if the Big Bang was not the beginning? What if it was just a transition from a previous phase? This is the idea behind several cyclical models of the universe, one of the most prominent being the Big Bounce. In this view, the universe goes through an endless series of cycles of expansion and contraction. The Big Bang was preceded by a previous universe that collapsed in on itself in a big crunch. According to theories like loop quantum gravity, as the universe collapses, the quantum nature of space-time itself creates a repulsive force. When the universe reaches a certain minimum size, an incredibly small but finite volume called the Planck scale, this quantum pressure becomes so strong that it halts the collapse and causes the universe to bounce. This bounce is what we perceive as the Big Bang. It is not a beginning from nothing, but a rebound from a previous cosmic state. In this model, the universe recycles itself on the grandest scale imaginable. An entire universe lives for trillions of years. It expands, forms stars and galaxies, and eventually dark energy might decay or reverse, causing the expansion to slow, stop, and reverse into contraction. All the matter and energy in the universe would rush back together. Galaxies would merge, stars would be torn apart, and everything would be compressed back into a hot, dense plasma. This big crunch would erase all the structures that had formed. The heat and density would break down all matter into its most fundamental particles. But it would not reach a singularity. At the moment of maximum compression, the universe would bounce, triggering a new Big Bang and the birth of a new cosmos. This is the ultimate recycling. Not just of atoms, stars, or galaxies, but of spacetime itself. Each new universe could be born from the ashes of the one before it, perhaps with slightly different physical laws or constants. The evidence for such a model is speculative, and it is at the very edge of theoretical physics. But it presents a compelling alternative to a single beginning and a final, cold end. It suggests a cosmos that is truly eternal, one that is constantly being broken down, remade, and reborn, a single, magnificent, and unending cycle of cosmic renewal.